you eventually reach a point where they become wave packets. So the Schrodinger cat collapses each case into a wave packet. This is taking its time. And you end up with wave packets instead of a Schrodinger cat. So this is now physically, so those of you who are familiar with the notions of decoherence, this is like the standard, this is the party line of what decoherence does, evolved very explicitly in this numerical form. So far it's just following the party line, and I've said nothing new, except got to advertise my particular toy model. And so here we have a sort of summary. The toy model successfully Einselects the class of wave packets from the Schrodinger cat superposition. So we started with the Schrodinger cat state and wound up in a mixture of two wave packet states. So that's all nice. Now I want to talk about the arrow of time. So what I was just showing you, so here's what the entropy does. And I was capturing a range of times where the entropy was doing this. And this is a very generic situation where every conversation I've seen about Einselection involves an arrow of time. So there's nothing new here either. The Einselection is about, for example, a product state turning into a mixture. The von Neumann entropy goes up when that happens. That's just the standard thing you do when you talk about Einselection. But now, because I have this easy to deal with numerical tool, I can go ahead. So whereas Caldera and Leggett cooked up their parameters and their analysis so it only worked when the entropy was increasing, I can just go ahead and say, oh, well, let's see how it looks over here. And to do that, I'm going to show you another movie.
Was time there unit to the oscillator frequency?
The oscillator frequency is 2 pi in these units. So almost.
How big is the bad Hilbert space?
600. It's what I could get on my computer easily. Movie D. So I did this because otherwise the file was getting really huge if I put all the movies in one. So now I'm going to look at something in equilibrium, and here's what I see. And this is kind of consistent. We're saying, well, yeah, it's just noise, it's just junk. And that is kind of the party line. That's sort of consistent with saying, well, maybe we really do need an arrow of time to talk about classicality and Einselection. And indeed, movie D exhibits just the behavior you expect, and you might even call it colliding Everett worlds or maybe wallowing Everett worlds. So if you're an Everett worlds kind of person, you tend to think of this going from pure Schrodinger cat state to mixture of wave packet states as the branching of Everett worlds. And then you might well wonder in equilibrium, so the way Everett worlds always get to branch out is due to the arrow of time, due to the fact that you have the capacity for the von Neumann entropy to continue to increase as the system evolves. And you can, so it seems intuitive to think that when you run out of that capability to keep branching out, and when you've used up your arrow of time and you're at maximum entropy, that the Everett worlds will just as much branch out as branch back together, and so you'll lose that feeling that the stuff that you believe is isolating, is sort of pulling apart the different wave packets. So colliding and wallowing Everett worlds seems like a good description. So this again, follows some nice intuition about what might be happening with decoherence. But there's a catch. And the catch is that I actually showed you a result from different parameters than I was showing you before. So now let me go and show you another movie which is the actual parameter. So this is now a continuation of what I showed you before, with the into the equilibrium zone. So here's movie E. So this is now the real continuation. So everything I showed you, the collapsing hat, was happening here. Now I've extended that exact same physics outward into the maximum entropy zone. And interestingly, there's definitely remnants of this oscillating wave packet. It's not perfect. It's not a perfect wave packet, but it's oscillating still. And so to me, that's really intriguing. And it's kind of where I am. So this is a really new project, and I've just sort of arrived at this point, and there's lots of interesting work to be done, so you sort of get to the bottom of this and interpret it more fully. But, oh, I see I've totally lost my microphone. So I was really hoping to get a recording of this. So you get to hear my well, maybe I'll do this.
Yeah, it's recording me at this time.
Okay, and then so it picked up every footstep, I assume, as it was dragging along the floor. Okay, good. So this now is this very interesting situation that's intrigued me. So there seems to be a degree of classical behavior that persists into the equilibrium zone, which now going into this project, I could argue it either way, which is part of why I was attracted to playing around with a toy model, to kind of force myself to sort of come to grips with these things. So we can, and hopefully there'll be people here who are interested in this, and we can talk about how to argue it either way. And I want to learn better about how to dial the parameters and get, understand better how this phenomenon all emerges. But this is where I'm going to leave it. So this is all I have to say right now. I have a toy model that can do this. It's intriguing. And so I'd say, yeah, so that's that bullet point. And so I've now coming to the takeaways from part B of the talk, which is the sign selection thing. So I've created this toy model. It has some nice features. I've already advertised those to you. And then I will just say the relationship between Ein selection and the arrow of time is non-trivial. It's not the simplest possible thing, which would be that you don't have Ein selection if you don't have an arrow of time. And so features of Ein selection can remain even in equilibrium. What that has to say about the larger goal of bringing the arrow of time and into the emergence of classicality and relating it to cosmology, I don't know yet. I think there's lots of ways that can still be very interesting, but I just want to leave this as a provocation, really, for further discussion. And that's the end of what I have. I think I've put all the takeaways for both parts on a final slide, but I'm going to end there, and I'll let the organizers decide. I know I've kind of used time loosely for this talk, but we can do whatever the organizers want at this point. Thank you.
Question for you. So
Yeah.
At the end of this thing, it still has some structure that looks like a wave packet.
Yeah. Yeah.
And at the same time, say you're in the limit where the entropy is maximal. And those are completely incompatible statements. Like if the entropy is maximal, it won't look like anything other than a maximally entropic state.
Well, I'll show you my model.
Okay.
Yeah, I mean, yeah, so it's interesting. I mean, so what do you mean by maximal? This is just showing you the state. So the entropy is the entanglement entropy. And so it's saying, now one thing you can ask me is, so there's 30 eigenstates of the density matrix. What do the other ones look like? And some of them won't look like a wave packet. I'm quite sure. But this gets to the heart of what are these tools? What, I mean, I have utter confidence that this is mathematically correct, and we can discuss what this means. But yeah, all you need all you need to get maximal entropy is to have 30 orthogonal states as eigenstates of the density matrix, and they can perfectly well be localized states. That's the.
Is this a non-integral model? Are you really exploring the entire Hilbert space?
Well, there's a fixed energy, and it's not, so.
Yeah, you just had a bunch of symmetries, right? So you're definitely in some fixed energy subspace.
Right.
And the question is whether you're really getting kind of far random within that, or you're in a much smaller subspace because you have a bunch of additional symmetry.
So I don't know how to answer that, but I'm not particularly expecting to get Haar random. I mean, this is built as a physical thing, not as an attempt to do scrambling. So I don't know. So Haar random is something very different than having 30 equal eigenvalues, which is all I need to get maximal entropy for this.
Well, I mean, in the large n limit, it becomes the same thing.
Maybe so. That would be an interesting conversation. I mean, right. So, but I would say more generally, one of the things on my mind is, what do I need to be careful about that this is a finite system versus extrapolating to larger things. But it seems very physical to me. I think some aspects of this seem like they're. I mean, let's talk about a bowling ball hanging from a wire in this room in the air. We've got an environment. We've got a system. Yeah, eventually the bowling ball will sublime. Is that the Haar random thing you're talking about? Maybe. But until then, it's not. It's still a pendulum. It's still a bowling ball, and so this is more like that. I've not. The SHO is a fundamental degree of freedom. It's not going to sublime.
If you have like approximate conserved quantities, you will hit metastable equilibrium states on shorter time scales. So if you think about the bowling ball not sublimating, so that it keeps together, and it will do that on some fairly long time scale, then the whole system will equilibrate in a metastable state over that time scale, and then eventually the bowling ball sublimates and the room hits true equal, right?
So there's all these things, right? So I would just say that's a conversation to have about this. But yeah, other questions? Yeah.
So I'm interested in processes that happen after thermal equilibrium but before complexity equilibrium. And so what is
thermal equilibrium? Maybe you'll tell us.
Thermal equilibrium is when you get all the two-point functions get scrambled, and complexity equilibrium is when all the n-point functions get scrambled. As in when the other system becomes Haar random rather than just this much.
Other meaning the environment here?
Yeah.
Yeah.
Rather than just being maximum entropy. So Haar random is a much stronger condition because it. And so I wonder if this. This is completely speculating, whether if you ran it for an exponentially long time, whether you'd still get the same effect, or whether this relies on the environment being in thermal equilibrium, but not complexity equilibrium.
So another great conversation to have. One of the questions I'm hoping to get answered this week is the relationship between all this interest in complexity and Haar randomness and the no cloning theorem, because I don't understand why physics should care about Haar randomness, except in these curious ways that you're working on. So what that topic does for me is it makes the kind of stuff you're doing with Lenny and so on really exotic, in the sense that I can't think of practical ways in a lab where I care about Haar random. And it sounds like you're proposing some brand new way that physics actually does care about that, which is really intriguing. But I'm curious, I'd be curious to see you push back on that. I don't know, do you want to push back on that? Do you say, no, that's exactly right? Or, I'm offering that as, not that you have to give a snap answer, but you're welcome to if you want. But I'd love to have that conversation with you this week.
Okay. I won't do radio talk by answering.
Sorry, you won't? Okay, okay. But I look forward to that.